All right, we're going to get started with this week's seminar. Thanks everyone for being here, either in person or online, of course. We're enjoying the cookies and look forward to getting to share cookies with more people in the near future. So this is the second week of our seminar series, and this last week we got to hear from a bunch of faculty about all the fun stuff they've been doing recently, and this week we're going to hear about all the fun stuff our graduate students did over the summer, and with some of their some of the internships and summer programs that they participated in at the national labs. So we have, I believe, six presenters. We're going to try to keep it on schedule. So please, if you're presenting, keep it on schedule. And we'll start off with Arjun, Earth Person, is going to go first and talk about whatever this means.
Oh, yeah.
I don't know stuff. So,
yep. Sounds good.
So
right.
The floor is yours.
Thank you. I just need to figure out a clicker for a second. So
yeah, just use the space bar.
Oh, okay, gotcha. Yeah, perfect. That simplifies things. All right. Hi, everybody. I'm Arjun. I'm a second year grad student, and currently working on the reliability of autonomous control systems in the PRA group. So that's Dr. Diakonisa's lab. Over the summer, I was interning at INL as a continuation of the effort in this research space. And I know the title is like really wordy here. I mean, it's pretty long. Hopefully by the end of this presentation, you will have some understanding of what some of these terms mean. I have also tried my best to keep the definitions on every page because I get lost pretty quickly. And this thing is not doing the thing. Okay, there we go. So as I was saying, this is a continuation of the ongoing work. This is part of an LDRD with INL. This is part of the fission battery initiative at INL. And so the objective is to develop a R&D method for successfully enabling the reliability calculations and modeling of autonomous control systems. And in addition to that, for adversary human action. So that's in the space of cybersecurity. Well, that's fine. And so, so a lot of terms here. We're looking at what a fission battery is. Essentially, INL defines a fission battery as a fission reactor with some other attributes, such as being economic, which is to say cost-effective and throughout the entire life cycle, standardized in the sense that it should be modular and should be able to link together with other things, and deployed easily. And then installed, which means you can deploy it and just like forget about it. And of course, unattended, which means once you deploy it, you can just kind of walk away from it. So it could be in a container or something like that, and you just walk away from it. And this is moving by itself. And reliable, which means hopefully you don't have to come back to fix it. And so what is the motivation for doing this? Well, if you want to build anything, I mean, that's nuclear, you need to follow the licensing requirements, right? And the NEI 1804 document provides guidelines. So there's a non-light water reactor draft that is, well, that provides the guidelines. And so part of that is to perform a PRA, which is the probabilistic risk assessment for a fission battery. And when we do that, we want to make sure that we make realistic assumptions about our system. And so part of that is to model the control system reliability as it is. Since I said it's an autonomous system, it means that it's going to run on its own. There's going to be no human operator in the loop at any given point in time. Maybe apart from maybe installation and then end of life stuff. And so historically, this type of work has been done for, let's say, space applications by doing rigorous testing. And so that's true for, let's say, if you're sending out like a satellite or something in space. And in that case, you will do a lot of testing before you, send out your satellite or rover out in space. But oftentimes that's not possible and it's expensive. So we can do something else, which is simulation. And that's the core of this particular research. And so what we're simulating here is a fission reactor. This is from 2004. It's called SAFE 400, which is the Safe Affordable Fission Engine. And this was built by NASA, for NASA by Los Alamos. And it's used for propulsion, but it contains in it a 400 kilowatt. This is going to keep doing that, so sorry about that. So it's a reactor with control drums to moderate the fission rate. So as opposed to a typical reactor that you may have seen that has control rods, this thing has control drums, which means instead of moving linearly, it moves axially. And so as you can see on the diagram, there's some B4C, right? All right, so that's our system. But we want to be able to control the system. And so if we want to control the system, we need to come up with a control model. Always one step ahead. And so in this case, the plant is the control drum or set of control drums. In this case, it could have been 5 or 6 control drums. And we have a typical classical controller, which is a PID controller, which is a proportional integral derivative controller. And in this case, it's cascaded together with a high-level input which says, look, I have a reactivity target. I want my reactor to be at a certain reactivity at any given point in time. And I want to do that by mediating the control drum position. And so that's the first PID that you see. The equation here comes out of the work of Dr. Shannon Bragg-Sitton from, again, 2004. And so this model is built around that logic. And so we can go from reactivity to control drum position to the actual motor drive signal that moves the control drum in position. And so that's the system. Now we need to talk about what are we doing. Typically, a PID controller is not implemented as one thing on a computer, or on your autonomous control system. Typically, it's part of a PLC that's running hundreds of PID loops at any given point in time. And that's ultimately modeled as computer hardware. And so if you want to be able to capture failures at the controller level, we want to be able to look at, well, what's the code, what's the hardware, and how do those interactions happen? And so this is a typical pipeline that we have kind of seen over here. So you start with the source code. So that would typically be the logic diagram or the source code for a PID controller or a set of cascaded PID controllers that you compile into hardware-specific assembly instructions that's dependent on your machine. So that's, if you're running it on your home computer, it would be an x86 processor. So if you're running it on a Raspberry Pi, it would be an ARM processor. If you're running it on a PLC, it would be specific to the PLC's logic. And you compile that, and you can, and using this tool called LLVM parse, which is also part of the DPM methodology, we create what is called the DPM model. As an input, you also need, so it converts everything, all the assembly to failure models. And for each instruction at that assembly level, you provide a failure rate. So an addition operation, for example, may have a lower, I could argue, failure rate than a multiplication operation. Why? Because addition requires maybe orders of magnitude lesser number of transistors to implement than a multiply operation, but it depends on what is implementing it. So this is good because either as an analyst, you can provide this information, or if you have this information available from a manufacturer, that's already available to you. I mean, Texas Instruments builds billions of transistors, billions of CPUs that run for billions of hours. They have a very good understanding of how their systems fail in ambient or nominal conditions. And from that, you go to the DPM model, and I'm going to show you that next. So with all of that, what we get here is just one half of the DPM model. It's all the relationships between all the instructions. So if you don't look at assembly, don't worry about this. It's a lot of move operations. Move the data here, move the data there, etc. Anyway, it's there. I just wanted to show you that. And when all of this is done, oh, I should also mention, over here, we were only modeling the PID controller. There's also the entire control drum. We haven't modeled that. Modeling the control drum requires further analysis. You have to look at the physics of failure models. You have to look at the mechanisms by which it would fail. And so statically, we have performed some analysis here using a simple fault tree. This is done on an in-house tool that our lab is building. It's called OpenPRA. You can access it at openpra.org. It's free to use, and if you want to develop software for us, that would be awesome. And so that's for the control drum side. And now we put everything together. So I haven't mentioned anything about Emerald. Emerald is tool that essentially performs dynamic event tree analysis. And we link DPM to Emerald, and we map it from the failure space to a function space. Meaning the cloud that you see in red is showing us that DPM is mostly interested in the failures in the PID controller. And the failures there happen because they are affected by perhaps the ambient temperature, because computers or transistors or semiconductors are affected by temperature, and the flux in those areas. So if you can instrument your PID controllers appropriately, you can measure the flux, you can measure the temperature, and then on the fly, get a new failure probability for your PID controller. And as you saw, the system itself was pretty complex, so you can't like directly make that assumption. You have to run the model and get some results. One thing to mention here is that this is all based on discrete time Markov chains, which means it suffers from what is called state space explosion, which means you get too complex of code, and then now you're waiting until the end of the heat death of the universe and all of that. So you don't want to do that. But so there's some part there where you have to be careful as to how you design it. But what you get from Emerald, all Emerald asks is it asks questions in a very functional sense. It says, look, I want a target reactivity. What is the likelihood that I will get that target reactivity? And based on that, Emerald will then decide how to branch next in its event tree. This is standard in PRA. So that's the model, and this is ongoing work. There's a lot going on right now. As I said, this is the first year. There's at least a couple more years of this work. We're going to continue doing that. And I've skipped a lot of slides, but here we are. Oh, so finally, I just wanted to mention all the people who are on this call. I think the team from INL is online and on the call, so I want to thank everybody. I want to thank Courtney and Steve and Troy and Thomas and Bree and Professor Diakonisa. And I also want to mention Daniel and Lakshita, who have been working on this project. They were interns at INL, they're undergrads here, and they're not here today, but they've been working a lot with interfacing the code and making sure that it all works. And to ask like how the virtual internship experience was, I mean, it was really fun because I was here over the summer and my entire lab just hung out. And that's kind of how it was. So thanks.
Any questions?
Yes, questions.
And we're between last week and this week, we're going to work. Okay. If there's not any questions, then we're going to move on to stay on schedule with our next speaker. Vincent Novelino. Who was at Lawrence Livermore. So Vincent.
Alrighty, so I'm Vincent Novelino. I worked at Lawrence Livermore National Lab this summer under the Weapons and Complex Integration Division with Patrick Brantley. I am a second-year grad student here working under Dr. Anastrada doing computational neutron transport. And so this summer, I've been working specifically on running Monte Carlo simulations using this code called IMP, which is developed in-house at Lawrence Livermore. And there we go. And this other code called Maestro, which is a workflow manager, which I'll get to what exactly that is in a little bit. But that's also developed by Lawrence Livermore, but it's open source on GitHub, so you can go use and look at it. So what is stochastic media transport? I'm going to give some examples here that kind of motivate it, and then we'll move on to what exactly it is. So I give the classic examples there is inertial confinement fusion is where you could use this. And so what that is you have a pellet of deuterium, basically solid deuterium, and there's tritium gas inside. You stick it into this machine called a inertial confinement fusion reactor, where there's laser beams that shoot at this pellet, causes it to implode, and then as it implodes, it starts to fuse and produce energy, and then it will explode. During that process, however, if there's any sort of imperfections in the manufacturing of that shot or asymmetry in the way that the laser is delivered, you can create something called Rayleigh-Taylor instabilities. Basically, you get turbulence in your shock wave that's produced. And that leads to the stochastic distribution of your shock wave front. And in order to capture that modeling of that phenomena, you want to be able to introduce the stochasticity into your simulation. So that's kind of the motivation behind it. Another example, and I wish Dr. Blotnoff was here because it really relates to what he does. So modeling of BWRs, if you have bubbles rising within your reactor, those are going to be stochastically distributed within that reactor. And so your computational neutron transport code doesn't usually account for different bubble sizes, doesn't account for your void fraction. It may only account for your void fraction actually, but it doesn't actually account for the way those bubbles are distributed and how that affects your neutron transport calculations. And so that's the motivation behind looking into stochastic media transport. So to give examples of some of the ways in which we try to account for it, the classic way is you essentially average your properties together. What I mean by that is you have some volume fraction of your materials and you multiply fraction 1 times the material property that you want to investigate of 1, and then volume fraction 2 times material property of 2. And you add them together and that gives you your mixed or atomic mixed model. Another option is, and this was developed by Gordon Olson in 2007. He did this specifically for the set of examples he was investigating. Was he took a 2D model of basically material randomly distributed in cylinders and was looking at the transmission through a slab. So you're looking at the transmission through that stochastic media. He took those results and then performed a least squares fit to find an opacity, which in neutronic sense is a cross section. So we're talking about photon transport here, where it's an opacity. Neutronics, the equivalent is a cross section, just so you guys understand the language difference. But he used a least squares model fit to those 2D results in order to get an opacity. And then he used that 2D result least squares model to give a 3D opacity to use in his calculations. That would give the same transmission factor as if you actually modeled the 3D stochastic media. That's one way. The other way is what we did was we took essentially the characterization of our stochastic media. We said we have a box. So we have a box with a bunch of spheres distributed in it. We have a specific volume fraction for this box, and then we randomly distributed spheres within the box, and then ran a simulation. Took another set of random distribution of spheres in the box, ran another simulation for however many times we want, and then ensemble to average the results together, and that gave us a benchmark value. That's one way of doing it, but that requires running n number of realizations that you don't know if you're going to end up converging to a solution quickly or not. The other way, and this is a little bit more different of a way, is to do something called chord length sampling, which essentially is if I'm a particle traveling through my media, I am essentially looking forward in some distance and sampling the mean based upon the mean chord length that I'm going to travel, a mean path length in that specific medium. I sample a distance in there. I move to the edge I move to the edge there, record my tallies along the way. Then I switch materials. I sample a new distance to collision or distance to new material. I then move to that one and continue until the particle dies because of Russian roulette or whatever variant reduction schemes you want to use. That's one. So those are the three, that gives you 5 different ways to go about modeling your stochastic media. And the ultimate goal was to evaluate those core length sampling models relative to some benchmark results that we generate. To generate these benchmark results, we use something called Maestro. What Maestro is a high-level program written in Python that allows you to stick in some data, so some parameters, and then generate parametric studies on the fly for your batch system of interest. So anyone here run on RDFMG? Okay, so that uses the Slurm batch system, so it has a certain set of commands to it. Let's say you go to another lab, you go to another university, they have a different batch system. Well, what do? You have all these ad hoc scripts that you've written to run your parametric study on using Slurm as your batch system. And now you have to go and re-implement that code again for a different batch system. And so what Maestro does is it abstracts away your batch system and allows you to generate these parametric studies independent of the system you're running on, and then submit essentially the job to Maestro and generate the results. In addition, it allows you to extend a basic parametric study by allowing you to create something called a pgen file, which is essentially a parameter generator. And that allows you to create custom lists of parameters to pass into Maestro that will then generate the Slurm run scripts and run all the simulations you want to run and get the results. And then you can call your script at the end to go through, scrape the data, produce some pretty plots, and Bob's your uncle at that point. You got stuff to put in the presentation or in a paper. And so I showed that right here. This is what I show. I ran 5 different realizations of spheres and boxes. I ran them all together. I then ensemble averaged the results together, and then I produced this plot right here, all using Maestro and a couple scripts to facilitate the plotting and data scraping. The nice thing is that it's machine agnostic. So if I wanted to run this on a different batch system using the same code, I can do that, and it's easy. There was one issue that I'd like to mention, and that's running on Sierra-type machines, and that's a machine specific to Livermore, but also these LSF batch systems are going to be deployed on any of the new exascale machines. So progress from this summer, I show some videos here of a simulation of an experiment that based upon an experiment that they're running at the National Admission Facility, also known as NIF at the lab. And so you have photons that are streaming in here from a constant temperature source, and they're migrating through. And you can see the different spherical inclusions there, and you can kind of see here where some of those spheres lie in this 2D slice. Because the photons essentially are getting blocked by the spheres and absorbed in it more generally. And so that's one of the things that I was able to do using Maestro and then the stochastic media transport framework. So specifically what I ended up doing was for IM, I generated a 3D deck to run the E3D problem that was published by Gordon Olson to compare to. I did the same thing for the shock tube 3D, which is this experiment right here. And then I also investigated running the E3D problem on GPUs and assessing the performance there. We had some issues because essentially you run out of memory on the GPU when you ran too many particles, but in order to get a speed up, you had to run a lot of particles. And so we kind of put that to the side and focused more so on the shock tube and the E3D problem. And I'll show you why in a minute. Why that's the case, because we have results here for 2 different opacity and equations of state models. And so we have a constant opacity, so your opacity is set at a constant value, but a Marshall equation of state, which essentially is an ATQ relation to for your specific heat. over here, you have a temperature-dependent opacity, which is some constant divided by T squared, and then a constant specific heat result. And what you're seeing here is that these different CLS algorithms, Livermore Pomeranian and local realization preserving, perform very well to match our benchmark results for this temperature-dependent opacity case and for this constant opacity and Marshall equation estate case. However, it does not match the results that were published in Gordon Olson's 2007 paper. And the more reason is because his paper uses a diffusion model, which doesn't really capture the effects of basically the anisotropy in the problem and the fact that this problem is a pure absorber. So it's not actually diffusive in nature. And so these results obviously are going to be different. And we've confirmed the differences using an independent code called COLT. I want to thank you guys for taking the time to listen to my presentation and open up the opportunity to ask any questions.
Did you work for any specific applications or just like exploring the phenomenon by a good way to model it?
So the specific application would be the Shock Tube 3D results for that experiment that they're thinking about running at F. So that's the specific application in mind. So it's more so, can we use this Maestro framework and can we use IMP in order to model this thermal radiative transfer problem for stochastic media transport? So that's really the question we're asking, and we got a resounding yes.
There may be a question in the chat.
Let's see. How do you decide the locations of the spherical obstacles? Okay, so there is it's called a fast RSA algorithm. I'm not intimately familiar with the details. But basically you start sampling the locations of spheres, avoiding any overlaps. And so you can't have any overlaps within the spheres, and you can't have any spheres that will cross the edge of the boundary. And so that algorithm works to ensure that. The specific code we're using was written by Dr. Nick Gentile back a long time ago, and we just happened to use it because it was easy to plug into our framework.
All right, let's thank our speaker. You ready for our next one? Yeah, he's online, I think. Yeah. Kingsley, you want to go ahead and share your screen?
Yeah.
Okay. So our next speaker is Kingsley Ogadioba. You all set?
Yes, I'm all set.
Okay, the floor is yours. You got about 10, 11 minutes, okay?
Hi, everyone. So my name is Kingsley Ogadioba, and for the summer I worked at Idaho National Laboratory under the supervision of Dr. Sam Bays on significant quantity production in small modular reactors. So as we all know about Idaho is a multi-purpose national lab in Idaho Falls. It has about 890 square miles of infrastructure with over 5,000 employees, including experts in different fields. And the figure on the left here is the ATR infrastructure building, which comprises of most of INL's nuclear research capabilities, which is the I guess the department in which my supervisor worked as well. And I was able to work with INL on for this project as a part of the University Partnerships program as an intern, which aims to develop and implement collaboration-based research between universities and institutions as well. Now, over to my what I did for the summer. Like I said, I worked on significant quantity production. So significant quantity is defined by the IAEA as the approximate amount of nuclear material for which the possibility of manufacturing a nuclear explosive cannot be exceeded. What this generally means is that they are trying to create a quantitative a value for an IAEA inspection goal. And the objective of this inspection is the timely detection of the diversion of SQs of nuclear material from otherwise peaceful nuclear activities like nuclear energy production to the manufacture of nuclear weapons. Now, for different materials and for different isotopes, the SQ oil value is different. For plutonium, and this is the plutonium metal that contains less than 80% of 238 Pu, the value is 8 kilograms. For highly enriched uranium, this value is 25 kilograms of uranium 235. And for helium, which is higher enriched uranium, which has less than 20%, 235, this value increases to 75 kilograms. We should take into note that the significant quantity as described here also takes into account the unavoidable losses that comes from conversion and manufacturing. So it's not just a determination of a critical mass. Now, the reactor concepts that we worked on for our significant quantity production were SMR reactor concepts, and these were developed from publicly available literature. Now, the emphasis for the project was on highly field concepts, and also it emphasized self-contained integrated modular designs. Starting from the top left here in my figure, we have the AC 100, which is an integral advanced modular SFR. The integral here means that the pumps and the heat exchangers are all mounted inside of the vessel. The power rating for this reactor is 160 megawatts thermal, and the nominal cycle for the AC 100 is 20 years. So it will take 20 years before it requires refueling. Also, another fact about the AC 100 is that it was designed to be a breeder reactor, and the designers quoted that the plutonium production in one AC 100 reactor would serve for other AC 100 reactors as well. The next on the right is the new scale, which is a PWR type reactor with 260 megawatts at most. It has 37 field assemblies, and its nominal cycle is 2 years before refueling. Also, the new scale, while it does have a PWR geometry, the fuel rods in the new scale are half of the of what a PWR fuel rod length is. On the bottom left, we have the XE100, which has a 200 megawatt thermal power rating, and it's a high temperature gas reactor, and it's an advanced homogenizable bed type ATGR, which basically consists of a neutron reflected beam comprising of spherical few pebbles, which contain about 19,000 particles per pebble. And the cycle for this reactor is 3.5 years. Now, the final reactor on the bottom left, which is a difference from all the rest, is the Toshiba 4S. While it is an SFR as an AC 100, its power rating is 30 megawatt thermal, and its size is also very small in comparison with the other three reactors as well. It's an advanced modular SFR with a reflector controlled metallic fuel core, and the core lifetime is 30 years as well. Now, an anecdote here that I would like to share with you guys from Dr. Bates, while he worked on this, is that he says that despite multiple proliferation resistance claims, there is not yet a systematic comparison across multiple advanced reactor technologies. This is evident because of the different advanced designs, and they all try to basically go for one characteristic and use that as a proliferation resistance claim. However, these claims are only for peaceful use of nuclear systems. There is no accounting for like a breakout scenario where a state decides to use its inventory for nefarious reasons. Now, to quantify our significant quantity, we have the conversion ratio, which is basically the facial inventory production ratio to the facial inventory consumption. The models that we developed for this work were done with serpent, and serpent calculates its estimated CR based on the sum of all the reactions that produce the fissile isotopes, and then divides it by other reactions that remove fissile isotopes. From this computation, we can see that the ARC 100 has the highest conversion ratio of all the reactor concepts. This is expected because, like I explained before, the ARC 100 was designed to be a breeder reactor. Also, I failed to mention that serpent also accounts for in-situ burning while calculating its conversion ratio. Now, the results from the distribution calculations of these reactor systems, and from the figure on the top left, you can see that the plutonium production, the SQ for PU, is higher for the ARC 100. Like I said, this is also expected because of the high CR value of the ARC 100. And following this is the new scale plutonium production, which also has the second highest conversion ratio. Something to note here is that the XC100 has a very low plutonium production, and as evidenced by its conversion ratio. However, for the Toshiba forest, which has a comparably high conversion ratio, its SQ production for plutonium is very low in comparison with its initial fresh fuel loading. This is probably due to the small size of the reactor, which leads to like a lot of leakage, and the initial helium loading of the Toshiba forest is used to sustain criticality over the 30-year lifetime of this nuclear reactor. Now, normalizing the results in the bottom figure here by taking into account a developing nation that has like an annual requirement for energy, we can see that the orders of magnitudes for the ARC 100 and the Toshiba forest reactors are higher than the NuScale and the XC reactors. Like I explained earlier, this is also due to the increased core lifetime and then increased initial fuel loading. However, as we round out to about 20 years, we also noticed that the plutonium production for ARC, NuScale, and Toshiba were closer in magnitude to each other, with the value for the XC100 being like another of magnitude lower. This leads to certain conclusions. We understand that our plutonium production is a function of our power level, our initial helium inventory, and the conversion ratio. The long life reactor designs, the 20 and the 30-year reactor designs, require higher than normal helium inventories, and thus they also create higher than normal plutonium inventories at the end. Now, the HETR, with its smaller the conversion ratio and SQ production, if a state wants to misuse its inventory, it stands to reason that they would rather lean towards enrichment services as opposed to using the plutonium inventories. However, for SFRs which have higher CR and SQ production, state misuse is leaning towards plutonium diversion. This is important because it helps to state where the IAEA safeguards are going to be put in place in order to monitor and detect these kinds of misuse for these different reactor designs. And furthermore, the work is also improved to include other SMR reactor designs like the U battery, as well as the Russian icebreaker reactor, which converts HALEU to LEU reactors. Thank you very much. Any questions?
Any questions for Kingsley? So while our next speaker is getting set up, Kingsley, what nuclear powered Russian icebreaker reactor sound terrifying? What exactly are you going to do with that?
Oh, what?
The Russian icebreaker reactors, what exactly is going on with those? That's just sounds interesting.
Yeah, so it's as it sounds. It's basically a I would try to define it as like a nuclear battery out in the boonies or out where there's no a connection to the grid, and they used high assay LEU. But now the Russian government is trying to convert those reactors to LEU reactors for commercial use. So that's why those reactors are important to look at as well.
Interesting. Thank you very much.
Yes, thank you.
Any other questions? Okay, our next speaker then is Andy Rivas. About 10, 11 minutes. All right, all yours.
Thank you. All right. Good afternoon, everyone. Thank you for being here this afternoon. My name is Andy Rivas, and today I'm going to be presenting to you all the work I did over during the summer at INL, specifically considering the nuclear data uncertainty propagation for the versatile test reactor, or VTR. I did this work under the direction of Dr. Nicholas P. Martin, and my advisor is Dr. Ho, who's in the back today. So quickly to go over the outline of this talk, first we'll go over a little bit of background of INL, then we'll get into an introduction of the work that I performed, go over a couple of core characteristics of the VTR, so that when I say VTR, we all have a picture in mind of what the VTR actually looks like. Then we'll go over the uncertainty propagation methodology that we employ to calculate our uncertainties, and then finally results and conclusions. So beginning with some background with INL. INL is one of the 17 DOE national laboratories which are spread around the United States. It is located at Idaho Falls, Idaho. And at INL, they have various different nuclear reactor projects. These include developing next generation nuclear plants, fuel cycle research, LWR sustainability programs, and developing high fidelity modeling simulation tools. The most popular of which, and I'm sure everyone has heard about it, is the MOOS framework. And just to go over quickly what the INL's mission statement is, it specifically is to discover and demonstrate and secure innovative nuclear energy solutions, other clean energy options, and critical infrastructure. So in the work that we performed over the summer, it was with this mission statement in mind. So what exactly is the VTR? Well, in 2019, the US Department of Energy announced its plan to build the Versatile Test Reactor, or VTR. The VTR is a sodium-cooled fast reactor. I'll get into more details of what that actually means later. And its purpose is to accelerate the testing of advanced nuclear fuels, materials, instrumentation, and sensors by performing irradiation testing at much higher neutron fluxes, which are currently possible with the LWR fleet that we can do these tests in the United States. Specifically, the fluxes that we're talking about are above 10 to the 15th neutron per centimeter squared. So in the process in designing the VTR, and designing any kind of system that safety is important, one thing that we always need to be considerate about is the uncertainty in all of the simulations that we run. Specifically, with any kind of simulation we run or anything that deals in reality, we will have uncertainty with our input parameters. These uncertainties in our input parameters will be propagated through our system model and will affect various system level parameters. An example of this is peak clad temperature during a transient. Various different input uncertainties include nuclear data, geometry, mechanical properties. The specific uncertainty that we looked into was nuclear data. Specifically, how does the uncertainty related to nuclear data affect our uncertainty in our K effective of our VTR core? And after we do this, we'll be able to look into what are the most dominant cross-section reaction pairs. An example of that is, let's say, U-235 fission. So here we have the VTR reference core, as shown here on the right. As I mentioned before, it is a sodium-cooled fast reactor. And in case somebody doesn't know what a sodium-cooled fast reactor is, it's what it sounds like. It's a reactor that is cooled with liquid sodium, specifically sodium-23. Sodium-23 is used specifically as it provides various benefits. This includes better neutron economy than when you compare it to an LWR. Sodium-23 has a higher mass number than hydrogen when we're considering light water. Because it has a higher mass number, it doesn't moderate the neutrons as much. So we're able to have the neutrons on average at a higher energy range. So when the fission events do happen, we get more neutrons on average per fission event, which is why we have a better neutron economy. Another benefit of using sodium as our coolant is that it has a large boiling margin, around 800 Kelvin. This allows us to operate the SFR at higher temperatures, which would increase thermodynamic efficiency. And because of this high boiling margin, we can also operate the system at a lower pressure, in essence, increasing safety margins. So specifically with the VTR reference core on the right, each one of the assemblies are color-coded with what kind of assembly it is on the right hand, with the legend. And in parentheses is the number of assemblies for that specific assembly type. What I want to highlight specifically, and we'll see why this is important once we get to the results, is the ratio between fuel assemblies and reflector assemblies, which is 66 divided by 114, which is about 0.58. So just for now, keep in mind that for the VTR, the fuel to reflector ratio is about 0.6. So now let's get into exactly how uncertainty is actually calculated. We utilize the sandwich rule, which is shown with the equation in the title with the S transpose D times S. S is the sensitivity coefficient vector, while D is our covariance matrix. So what exactly is a sensitivity coefficient? Well, it is the relative change in the responsive interest R due to a relative change in a perturbed quantity X. So R in this study is K effective, X are the various cross sections we're perturbing. D, as I mentioned before, is the covariance matrix, which we can obtain through various means. The easiest of which is just to read it into our Python script from the Camara 2.0 library. And what the sandwich rule allows us to do is if we perform a small enough perturbation, and we make the assumption that with the small enough perturbation, the response will also change with the linear response, then we can utilize the sandwich rule to collapse relative uncertainties in Camara with the sensitivity coefficients into a single value. That single value is the uncertainty that we're looking for. So with everything here, our covariance matrices are known. We get that directly from Camara. So now the question is, how do we get our sensitivity coefficients? And we got our sensitivity coefficients by utilizing two different codes. The first one was percent, which is a dedicated deterministic perturbation theory code that is used in the Argon reactor computation or ARC suite of codes. And serpent, which is a 3D continuous energy Monte Carlo code for reactor physics calculations. The reason why we picked these two codes is because they use two completely different methodologies. Percent utilizes diff3D and utilizes a more deterministic approach to calculate sensitivities, while serpent utilizes the collision-based history approach, which is Monte Carlo based. So the idea is by using these two very different methods, if we're able to find out our top 5 overall contributors and overall uncertainty are roughly equal between the two codes, then we can have more confidence in our results that they are actually correct. And on the left is just an example of what sensitivity coefficients look like. So that's specifically for the sensitivity coefficient for U238 capture with the response being K effective. you can see that it's negative throughout the entire spectrum. That's because if you increase the U2 capture cross-section, it will always, of course, decrease your K effective. All right, so up here, I have all the results between the top 5 rankings of the isotope reaction pairs that contribute the largest amount of uncertainty to the overall uncertainty. I have the results for both the VTR using both percent and serpent based sensitivity coefficients. And we also compared our results to other similar SFRs. So in the first and the second and third columns, I have VTR A and VTR B. VTR A are the results from percent using the sensitivity coefficients from serpent. VTR B are the UQ results utilizing the sensitivity coefficients from serpent. And then in the other columns, we have FFTF, MOX 3600, ABR, and Zipper 9. So the big thing that we found with this study is if you notice between all the other reactor types, FFTF and on, you see that the top contributor, the most dominant contributor is U230 inelastic scattering. While for the VTR, we find that the iron 56 elastic scattering is the dominant contributor. Why is this the case? When we did the study, this is the first time, this is at least that I've ever seen in literature, that U230 inelastic wasn't the dominant contributor. The reason is because of the field to reflector ratio, which is in below the reactor types. You can see as we go from left to right, that the field to reflector ratio increases from 0.58 for the VTR all the way up to 2.82 for Zipper 9. And as we increase the field to reflector ratio, we can see that the contribution from iron 56 elastic scattering begins to decrease out of the top 5 once you hit MOX 3600, when our field to reflector ratio is above 1. So in conclusion, in this study, we propagated the nuclear data uncertainties to K effective. We did a lot more responses, but just to keep this short, I just showed you results for K effective. We found that person and serpent agreed very well with one another. The overall top contributors were U230 inelastic, sodium-23 elastic, and iron 56 elastic, especially iron 56 elastic, being the dominant contributor for the VTR. And the difference, and the reason why we see differences between other reactor types is for the field to reflector ratio that I mentioned before. And the next step for this study is to propagate these uncertainties that we found here to the system level. So how do the nuclear data uncertainties affect our peak clad temperature once we have some kind of transient? And that's it. Thank you all very much. Are there any questions?
So are you only looking at sensitivity due to a certain data?
Yeah, we just looked at nuclear data across or uncertainty. Doing the other types of uncertainty, was a different study. But you usually start with nuclear data because that's the most obvious one. And that one is readily available. Versus if you do mechanical or geometry, what exactly are your tolerances for your clad? That's more debatable than the nuclear data uncertainty, which is readily available and you can compare a lot with other studies specifically.
Any other questions? Any questions on the chat? No. Okay, let's thank our speaker and we'll move on to our last speaker, Cole. Cole, if you want to, please share your screen. So Cole Takasugi. And good.
Hi. Hello.
And the floor is yours.
Okay, thank you. My name is Cole Takasugi. I am a PhD student working with Doctors Ivanov and Avramova, and I will be presenting on some validation work for the Griffin code that I did with Idaho National Laboratory, working with Dr. Nicholas Martin. So Griffin is a time-dependent finite element reactor physics code built within the MOOS framework. It supports a number of different methods, and is a recent evolution of the Mammoth code, which integrates features of Proteus. And it has a wide range of applications to a variety of different reactor technologies. So to give some context to the internship, the Monte Carlo code serpent is used at INL for generation of multi-group cross-sections that are used in Griffin. And it can also be used to generate reference flux at current for use in equivalence procedures such as superhomogenization or calculating discontinuity factors. However, applications of a serpent Griffin scheme to different reactor designs observed significant differences in the kinetics parameters between serpent and Griffin. So they would find delay neutron fraction and mean generation time would be significantly different between the two and produce some difference in expected transient behavior. So the goal of the internship was to assess how well Griffin preserves the kinetics parameters from serpent for various different modeling options, potentially identifying where these differences are coming from to inform future work and to validate these kinetic parameters with experimental results. So this slide shows a typical transient procedure for Griffin, generating cross-sections with serpent, performing an equivalence procedure such as superhomogenization. I'll talk about that on the next slide. Then eigenvalue and null transient calculations, an IQS transient, which calculates the core-wise kinetics parameters, so what we are looking at here, and then finally a normal transient. So superhomogenization or SPH equivalence essentially enforces preservation of reaction rates from serpent to Griffin by modifying the cross-sections that came from serpent. So it adds a factor in, as shown in this equation here. The important things to note are that it can be applied independently to different portions of the core, at least including all of the fuel-containing elements in order to preserve the eigenvalue. So the reason why I'm talking about this specifically is because they observed that the selection of regions for SPH equivalence had an effect on how well the kinetics parameters are preserved. So whether it's only in the fuel or also in some reflector regions, for example. So to evaluate the kinetics parameters, we selected the IPEN MB01 thermal spectrum research reactor. It's used in a reactor kinetics experiment as part of the International Reactor Physics Experiment Evaluation Project. It's a 26 by 28 array of rods with guide tubes and control rods inserted to a critical state. And this sits on a base plate in a large cylindrical reflector. And shown here are just the kinetics parameters and some reactivities corresponding to different periods, which we can compare against. So this is the analysis procedure I developed. Calculating group constants with serpent, collecting the data for superhomogenization, and serpent also evaluates the kinetic parameters. So we can validate the serpent model by comparing these kinetics parameters to the benchmark. Then we convert cross-sections to the format for Griffin, and then generate the SPH factors for Griffin, set up steady state forward and adjoint solutions to feed into the Griffin transient, IQS transient, which then collapses kinetic parameters. With the Griffin kinetics parameters, we can compare against the serpent ones to verify how well they are preserved, and then compare against the benchmark to validate the overall scheme. So this is based on the serpent model. I don't need to go into too much detail on it. The important things are that we repeated it for two different libraries, the ENFP 7.1 and 8.0, and generated cross-sections from it for 4 different energy grids, a 2-group, 4-group, an 8-group predefined one, and a 4-group energy grid that was refining the thermal energy. So the reason why we did this is because there was also an observation that somehow the number of energy groups was also affecting the kinetics parameter results. And then to permit SPH equivalence, a 49 by 49 by 44 lattice of detectors was implemented in the serpent model to collect reference fluxes. And this includes a nearby portion of the reflector region, but due to the low neutron count far away from the core, does not include the full reflector region. So shown here are the results of comparing serpent versus the benchmark. In the bottom left is the relative difference for different serpent methods. In general, they're performing relatively well. I highlighted the green ones because these are the ones which we are taking delayed neutron data for Griffin from, and we'll be comparing against. In the top right are reactivity estimates, which are not performing very well, but this is in line with other evaluations of this benchmark that use the ENDF libraries. So that it matches other evaluations is good. Then for Griffin, in addition to creating different model or different runs for each energy grid, there's also the considering SPH equivalence. So including the full set of lattice detectors, which included part of the reflector, applying only to the fuel, and then also trying without SPH. And then also whether or not it's applied in the adjoint step was also a consideration. And this totaled 40 different sets of Griffin runs. So this shows the results of Griffin versus Serpent. One important thing to note is that 2 of the energy grids perfectly replicated the delayed neutron fraction, while the others got between 7 and 10% off. The cases with SPH in the adjoint step tended to have, or without the SPH in adjoint step, tended to improve results. Then small numerical differences existed between the 2 libraries. And I'm not going to show them, but comparing the reactivities, Griffin in general preserved the reactivities very well because it's mostly based upon the delayed neutron data that is taken from Serpent directly. So why are some of them perfectly replicating Serpent? If we look at how Griffin is collapsing the delayed neutron fraction, is shown in this equation here. And when the spectra of prompt and delayed neutrons are identical, these integrals disappear, and the effective delayed neutron fraction from Griffin is equal to Serpent's. However, when we have different energy grids, such as the 4-group and 8-group predefined energy grids, this introduces a factor that caused the difference that we observed. So this is the main source of the differences, but also the SPH application was found to improve kinetics parameter estimates when only in the fuel and when not applied to the adjoint step of Griffin calculations. So to conclude, this is the Serpent Griffin framework applied to the IPAN MB01 reactor kinetics benchmark as a validation of the Serpent Griffin scheme and verification of Griffin's preservation of Serpent kinetics parameters. The major conclusion of this work is that the selection of the energy grid is extremely important in reproducing the kinetics parameters between Griffin and Serpent steps, and methods for optimizing the selection may be a subject for future work. Thank you.
Any questions? Fun reactor people, help me out. This wasn't a plasma talk. Any questions? Or I'm just gonna desk silly questions. Oh, Russian ice cards. Anything on the chat? I guess go into the, if I'm gonna try to combine this talk with the last talk, is there any, I mean, for uncertainty propagation? Is there anything you gotta worry about here that similar to the previous talk, or is that, am I missing something?
So if we're comparing to the benchmark, I think there would be, but since the primary focus is to look at how Griffin is preserving the serpent results since we're looking primarily at how well Griffin preserves serpent's results, it's kind of isolated from the full problem. I mean, we are trying to validate the overall scheme, but the main driver of the work is what is causing the difference. And we identified that as differences in spectra, delayed and prompt, which, yeah.
Okay. I know, like, I mean, we deal with codes with cross sections all the time in plasmas as well, and so the and just small changes in those cross sections, depending on what kind of model you're using, can give you just completely different. One can give you one wiggles like this, the other one can just kill you. I was wondering if one of these would be more sensitive to uncertainties than the other one. I mean, if you use the exact same inputs for both, and you get the same answer, that doesn't necessarily mean that one of them's not standing on the edge of a cliff, right?
Sorry, I couldn't hear very well.
That one of them might be a little bit more sensitive. If you put some uncertainty into the inputs, that one of them might have be more sensitive to those variables than the other, or is that?
Oh, right. So, serpent is where the uncertainties would come forth, and Griffin, all of the difference from the serpent results is, in this case at least, is due to the calculation. So Griffin should ideally be able to reproduce the serpent results here, but due to the assumptions in the models, it does not. So the uncertainties from the cross sections are coming to the serpent results.
Okay. Thank you. Anything else? Okay, thanks everyone for coming, and I look forward to seeing you all next Thursday for next week's seminar. Thank you very much.